Okay, let's unpack this. Have you ever paused to consider what intelligence really is? Not just the smart things we do, but the intricate dance happening behind the scenes in that incredible organ, your brain. Today, we're diving deep into some groundbreaking ideas from Jeff Hawkins. You probably know him, the visionary behind devices like the Palm Pilot and Trio. He argues that we've been fundamentally misunderstanding how the human brain works, which has, in turn, sort of hindered our ability to build truly intelligent machines.
Yeah, what's truly fascinating here is how Hawkins, alongside science writer Sandra Blakesley, really challenges decades of conventional thinking. I mean, in both artificial intelligence and neuroscience. They suggest that previous attempts to replicate human intelligence stumbled. Why?
Hmm.
Because they focused on emulating behavior without first grasping the brain's core function. So our deep dive today will help you understand not just what intelligence is, but why a new perspective on it could reshape, well, everything, from your daily perceptions to the future of technology itself.
You've shared some really compelling source material here, and our mission today is basically to extract the most important nuggets of knowledge from it, give you a shortcut, to being truly well informed about what Hawkins calls the last great terrestrial frontier of science.
Mm.
Get ready for some moments that might just rearrange your mental furniture when you think about your own brain. So, before Hawkins could even propose a new theory, he had to confront a pretty significant question, right? Why had a quarter century of scientific effort in AI, not yielded more? He even tried to join the world of brain science himself, only to find some, well, rather surprising resistance.
Oh, indeed. Hawkins, whose passion for understanding brains actually predated the advent of personal computers, he stumbled upon a significant disconnect. He actually proposed to Intel's chairman, Gordon Moore, that they start a research group focused on how the brain works. Can you imagine? But he was rejected by Ted Hoff, who believed it just wasn't feasible in the foreseeable future. And then even MIT's Artificial Intelligence Lab, which was seen as the mothership of artificial intelligence at the time, they turned him away too.
Wow. So, what was their reasoning? Why the pushback?
Well, their core belief was that you didn't need to study the biological messiness of real brains to understand intelligence. It was all about programming computers to produce intelligent behavior. That was the key word.
Okay, so that brings us right to the core fundamental flaw. Hawkins identifies with traditional AI, this laser focus on behavior.
That's precisely the point. AI, heavily influenced by Alan Turing's concept of universal computation and his famous Turing test, it essentially argued that if a computer could fool a human interrogator into thinking it was a person, then, well, it must be intelligent. The central dogma became that the brain is just another kind of computer, full stop. It didn't matter how an intelligent system worked internally, only that it produced human-like behavior, manipulating abstract symbols like words or, chess pieces.
And they got some early scientific backing for that idea, didn't they, from McCulloch and Pitts? They suggested neurons could act as simple logic gates, kind of reinforcing that idea that brains were essentially just electronic circuits.
Right, exactly. But what they didn't really ask was if neurons actually were wired that way in living brains. It was more of a philosophical position. And this stance was also sort of buttressed by behaviorism, which, as you know, ignored internal mental states entirely, focusing only on observable inputs and outputs. AI made these grand claims about quick success in areas like language translation and vision, but those breakthroughs largely failed to materialize.
Yeah, that focus on behavior really started to crumble under scrutiny, didn't it? I mean, one of the most famous challenges came from John Searle's Chinese room thought experiment. How did that expose the limitations of the behavior-only view?
Ah, the Chinese room. Yes. This argument, which famously caused a huge row among philosophers and AI pundits, it demonstrates that mechanically following rules and producing correct outputs, that's not the same as understanding. Like the English speaker in the room who doesn't understand a word of Chinese but can manipulate characters based on a rule book to answer questions perfectly. He's producing the right behavior, but he doesn't understand. Searle made it really clear. Whatever intelligence is, computers programmed that way don't have it in that sense. True understanding is an internal state, not just an external behavior. You can understand a complex story perfectly well just by listening quietly, right, without any overt action.
That makes sense. So after AI, neural networks emerged, and they seemed like a more biologically inspired step, maybe closer to the brain. But Hawkins found them equally flawed, didn't he? Why was that?
Well, they certainly were an improvement in some ways. Their architecture was loosely based on real nervous systems, learning by example rather than direct programming. So, better, maybe. However, Hawkins, he quickly became disillusioned. His key criteria for understanding the brain were One, the inclusion of time in brain function, and two, the importance of feedback connections, meaning information flowing not just forward but also back to previous layers. Most common neural networks at the time, like backpropagation networks, they processed only static patterns. They had no true feedback during normal operation and really no sense of history or sequence. Hawkins kind of compared them to simple transistor amplifiers versus a complex computer. They could do something, but not the main thing.
So they could do interesting things like maybe recognize patterns, but they didn't actually reveal how the brain works. Like his own experience comparing Nestor's handwriting system to his graffiti. Graffiti was simpler, more reliable, but not trying to be brain-like.
Exactly. Their fundamental problem, which they shared with traditional AI, was this over-reliance on behavior as the sole metric of intelligence. But, as Hawkins points out, and this is key, intelligence is not just a matter of acting or behaving intelligently. Behavior is a manifestation of intelligence, but not the central characteristic or primary definition of being intelligent.
Okay, so if behavior isn't the central characteristic, what is? And how does the brain actually work if it's not simply another kind of computer? So if behavior wasn't the key, what was? Hawkins had this pivotal aha moment, right? A really simple question about perception that led to his entire memory prediction framework. What was that question and what did it reveal?
Right. The insight came from a seemingly simple scenario. What would happen if a new object, let's say, a blue coffee cup, suddenly appeared in a room you knew intimately? Hawkins realized that to even notice something new, your brain must have expected everything else in that familiar room. It must have had a prediction for what should be there. This means our brains are constantly, relentlessly using stored memories to make predictions about everything we see, feel, and hear. And crucially, most of these predictions are unconscious. We're not even aware of them. It's when a prediction is violated, when something doesn't match, that it draws our attention. This is why you instantly notice if your familiar front doorknob has moved by an inch or if the door's weight has changed, like in that altered door experiment he mentions. Correct predictions lead to understanding, a sense of familiarity. Incorrect ones lead to confusion and a shift in attention.
Wow, okay. So what we perceive isn't just raw sensory input hitting our eyes and ears. It's a dynamic blend of what we sense and our brain's constant memory-derived predictions. That totally flips the script, doesn't it? It turns the brain from a passive receiver into a deeply active predictor.
Precisely. And if we connect this to the bigger picture, this idea fundamentally reshapes our understanding of the brain's whole operation. It's not a computer that computes answers through billions of sequential steps. I mean, think about the timing. The 100-step rule shows that neurons are actually too slow for that kind of massive serial computation. In the half second it takes you to recognize, say, a cat in a photo, information can only traverse about 100 neurons, maybe fewer. This strongly suggests the brain doesn't calculate answers on the fly. It retrieves answers from memory. The entire cortex in this view is essentially a vast, complex memory system.
Like catching a ball. That's a great example he uses. A robot would calculate trajectories, angles, speeds. But you, the human, you just retrieve a sequence of muscle commands from memory, adjusting it in real time based on feedback. It's all stored, not calculated from scratch each time. That's a profound difference.
And it really is. And this neocortical memory, it has 4 fundamentally different attributes from computer memory. Attributes which are absolutely crucial for this constant process of prediction.
Okay, what's the first one?
First, it stores sequences of patterns, not just static snapshots.
Right, like recalling a story or reciting the alphabet backward or remembering a song melody. You can only really do it in a temporal sequence, right? You can't just grab the whole thing at once or jump around arbitrarily.
Exactly. Second, it recalls patterns auto-associatively. Think of it like seeing just a tiny corner of a familiar photo, but your brain instantly fills in and sees the entire picture. That's auto-associative recall. It lets you retrieve a complete memory from even a partial or distorted input. A small detail can sort of activate the whole memory. It's how you fill in unheard words in a noisy conversation, for example.
Okay, that makes sense. And the third?
Third, and this one's huge, it stores patterns in an invariant form.
Invariant, meaning it doesn't matter how the input changes.
Pretty much. You recognize a friend's face, regardless of their expression, the angle you see them from, or the lighting, right? You identify a song no matter what key it's played in or what instrument plays it. The brain isn't storing thousands of exact changing sensory snapshots for every object. It's storing the underlying relationships, the spatial intervals between features for faces, the pitch intervals between notes for music.
That's a massive leap beyond what traditional pattern recognition systems could easily do, isn't it? It gets to the core of abstract understanding.
It absolutely does. And this raises an important question. How can the brain recognize something like a rake as basically part of your body if you use it for grasping? Or how can blind climber Eric Weinmelier see via a device on his tongue that provides pressure patterns? It's because the cortex only knows streams of spatial patterns flowing through time on axons. It doesn't fundamentally care where the patterns come from, whether it's eyes, ears, or a tongue device. It only cares if they correlate consistently, if they're predictable. As Hawkins puts it, predictability is the very definition of reality.
Wow, predictability is reality.
Okay. And finally, the fourth attribute, you said it connects the others. Yes. The fourth is that the neocortex stores patterns in a hierarchy. Your brain naturally discovers and stores hierarchical relationships in the world. Think about language. From recognizing letters, then words, then phrases, then sentences, or music, notes, then melodies, then entire songs or albums. Higher regions in the cortical hierarchy maintain the big picture context, like the concept of being at home, while lower regions handle the fast-changing sensory details, like fixating on a specific window latch. This hierarchical structure allows for efficient reuse of lower-level learned patterns or objects and enables understanding across different levels of abstraction.
So putting it all together, the brain isn't a calculating computer. It's a highly sophisticated hierarchical memory system. And its main job is constantly building and refining its model of the world by predicting the future based on past experiences, stored as sequences of patterns in invariant forms. Okay, so how does this memory prediction framework actually operate within the physical brain? Hawkins explains it by diving into the neocortex itself, right? That 2 millimeter thick, 6-layered sheet that makes up, what, 30 billion of your cells?
Exactly. And the key insight here, which was championed by the neuroscientist Vernon Mountcastle back in 1978, is what he called the astonishing hypothesis, which is that the neocortex is remarkably uniform in its appearance and structure across different functional areas. The part that handles vision looks pretty much like the part that handles touch or language.
Yeah.
This suggests, and this is huge, that the cortex uses the same computational tool to accomplish everything it does.
Yeah.
Well, no. So differences in function vision versus language, they seem to stem from what these regions are connected to, the inputs they get, not from fundamentally different internal operations.
So it's cortex's cortex performing a common algorithm, like a universal operating system for intelligence. What does that tell us about how information flows? You mentioned hierarchy.
It does suggest a universal algorithm, yes. And the flow is crucial. Information flows up the hierarchy that's called feed-forward. Think of raw sensory data moving from lower sensory regions, like the primary visual cortex V1, up through layers 4, 2, and 3 to higher regions. As it ascends, the representation becomes increasingly stable and invariant. You go from constantly changing pixels on your retina to a stable concept like face. But just as importantly, information flows down. This is feedback. This happens from higher regions, layer 6, down to layer 1 of the lower regions. And this downward flow is crucial for prediction. It allows those abstract invariant predictions from higher levels to unfold into specific expectations at lower levels, like knowing the interval to the next note in a song, invariant prediction, and combining it with the last specific note you just heard, current context, to predict the exact next note you expect to hear.
Ah, okay. So feed forward is the data coming in, feedback is the prediction coming down, and the thalamus fits in here somewhere too.
That's right. The thalamus seems to play a role, possibly acting as a kind of delayed feedback loop, which is actually similar to some autoassociative memory models that learn sequences over time. It helps coordinate things. And remember, the brain is constantly learning, so your memories for common objects and sequences like recognizing letters, then words, then entire phrases as you learn to read, they actually seem to move down the cortical hierarchy over time as they become more familiar and automatic. This frees up the higher regions to focus on learning more complex and subtle patterns. It's likely why a young brain might seem slower at some tasks. The necessary memories are still higher up. An adult's more practiced brain has pushed many basic recognitions down to lower, faster levels.
That makes so much sense. It explains why practice makes perfect, literally restructuring the brain. So this means that when an unexpected pattern arrives, say a jarring crash in the middle of a familiar melody, the error signal, the failed prediction, propagates up the hierarchy. It keeps going up until a region can interpret it or make sense of it.
Exactly. The more novel or unexpected the event, the higher up the hierarchy the information has to travel to find a pattern it matches or to be flagged as truly new. And eventually, it might even reach the hippocampus.
Which is key for new memories, right?
Precisely. That's why the hippocampus is so essential for forming new declarative memories. The kind of memories you can consciously recall and talk about, like what you had for breakfast or a fact you learned. It sits right at the top of the cortical pyramid, metaphorically speaking. It seems specialized in capturing this novel, unexpected information that doesn't neatly fit into existing cortical models. These new hippocampal memories are then slowly transferred or consolidated into the cortex over time, maybe through repeated experience or even just thinking about them, or they're eventually forgotten if they aren't reinforced. It's also why, as Hawkins kind of paradoxically notes, the more you know, the less you remember of truly novel events because your cortex can explain away more things based on past experience.
Okay, so the framework explains memory and perception, but what about the really big questions?
Oh,
Hawkins uses this memory prediction model to offer insights into creativity and even consciousness. How does creativity fit in if our brains are just memory prediction machines?
well, according to this framework, creativity isn't some extraordinary magical ability located in one spot in the brain. It's actually an inherent property of every cortical region, a necessary component of making good predictions, especially in novel situations. Creativity, simply put, is making predictions by analogy. This happens all the time, ranging from the completely mundane, like figuring out where the restroom probably is in an unfamiliar restaurant by analogy to others you visited, all the way up to the genius of a mathematician proving a complex conjecture by seeing an analogy to a simpler problem they solved years ago, or Shakespeare creating powerful metaphors by constantly seeing a succession of clever analogies between different concepts.
Huh. So it's not separate from prediction, it is prediction, just applied more broadly. So if I learn to play a familiar melody on a new instrument, say a vibraphone instead of a piano, that's a creative act because my brain sees an analogy between the piano keys and the vibraphone bars, applying learned melodic pattern sequences to a new physical situation. It's prediction by analogy, happening constantly, often unconsciously.
Absolutely. That's a perfect example. And you see this in art and science too. Great works often violate our predictions just enough to be interesting and teach us new patterns or analogies. They have that contradictory tension between familiarity and uniqueness. And Hawkins argues you can definitely train yourself to be more creative. How? By giving your brain time and space, trying to rearrange problems, look at them from different angles, or even literally flipping the problem around physically, as he did when inventing his graffiti handwriting system. Feed it diverse inputs.
Okay, but can this process lead us astray? If our brains are constantly looking for patterns and making analogies, which sounds like creativity, can that sometimes create false beliefs or reinforce bad ideas?
That's a really crucial point, and yes, it can. False analogies are a real danger. The brain is a pattern-matching machine, always looking for correlations. And it will accept false patterns or weak analogies if strong, correct correlations aren't readily available or learned. Things like pseudoscience, bigotry, and intolerance can be rooted in this tendency, finding spurious patterns or making harmful analogies based on incomplete or biased information. Even stereotypes, which are essentially invariant memories applied too broadly or judgment by stereotype, are an inherent feature of how the cortex works. It seeks simplified, generalizable patterns to make quick predictions. The way to combat their harm isn't to somehow stop the brain from making analogies, which seems impossible, but by actively teaching skepticism, empathy, critical thinking, and exposing ourselves to counterexamples to challenge those potentially harmful ingrained patterns.
That's a really important clarification. It's not the mechanism that's flawed, but how we apply it or the data we feed it. Okay, so what about the other huge question, consciousness? Where does that fit? Is it just a magical sauce poured onto the physical brain, or does this framework explain it?
Well, Hawkins takes a pretty direct, almost functionalist stance here. He contends that consciousness is simply what it feels like to have a neocortex. It's not some separate entity or ghost in the machine. Our everyday notion of being conscious, he argues, is largely synonymous with forming declarative memories, those specific memories of events and facts you can consciously recall and talk about later. Think about it. If you were to have your memory of the last 24 hours completely erased, even if others observed you behaving normally during that time, you would feel as if you had been unconscious for that period. You'd have no subjective experience to report. Now, the harder question, the philosophical problem of qualia, why subjective experiences feel the way they do, like why red feels red or pain feels painful, that's still a deep mystery. Hawkins suggests it might be tied to unique wiring in subcortical areas or connections to emotion centers. But his primary focus is on the function of consciousness as tied to memory and prediction within the cortex.
It's fascinating, though, that even things like imagining or daydreaming fit neatly into this framework. You mentioned layer 6 projecting back down. So when we imagine something, it's basically layer 6 cells projecting predictions back to layer 4 in their own columns, allowing us to sort of see or hear the consequences of our own internally generated predictions. It truly sounds like thinking, predicting, perceiving, and even doing are completely intertwined processes, just patterns flowing up and down this cortical hierarchy.
That's exactly the idea. They aren't separate modules. They're different aspects of the same fundamental memory prediction process unfolding across the hierarchy.
Okay, this all leads to the really big question, the practical application.
Yeah.
Can we finally build truly intelligent machines based on this new theory? And if so, what will they look like? Forget the sci-fi robots for a second.
Yes, Hawkins believes we absolutely can. But, as you hinted, they probably won't be the humanoid robots of science fiction. He sees those as generally impractical, costly, and kind of a historical artifact, a concept born more of the Industrial Revolution than biological insight. Instead, he proposes a recipe for building intelligent machines based on the cortical principles. You start with custom senses, specifically designed to extract the relevant patterns in the world for a given task. Then you attach a hierarchical memory system that operates on the same core principles as the cortex storing sequences, auto-associative recall, invariance, hierarchy, and crucially, you train it through observation and instruction, essentially exposing it to its environment, just like we teach children. There's no explicit programming of rules or large databases. The machine learns its own world model dynamically through experience and prediction.
Okay, so let's take an example. If you want a smart car, you don't program rules for every possible traffic situation. Instead, you give it cameras and radar, its custom senses tune them to extract patterns relevant to driving. Then you attach this hierarchical memory system, and you train it by exposing it to hours and hours of real-world traffic, allowing it to build its own hierarchical model of roads, vehicles, pedestrians, and make predictions about what will happen next.
Precisely. That's the approach. And the technical challenges, particularly capacity, which seemed insurmountable years ago, are becoming surmountable. A human cortex has about 32 trillion synapses, which is obviously vast. But Hawkins calculates that could, in principle, be replicated with the storage capacity of about 80 modern hard drives. That's getting within reach. But maybe even more importantly, silicon-based intelligent machines could potentially think much faster than biological brains, maybe 1,000,000 times faster, because electronic transistors are inherently so much quicker than biological neurons firing. Imagine a mind that could dedicate the equivalent of a month of human thought to a complex problem in just 10 seconds.
1,000,000 times faster. That's just staggering. It opens up truly mind-bending possibilities for what these machines could achieve. And once one system is trained, say that smart car system, it can be copied endlessly, just like software, right? Allowing for mass production of highly capable intelligent machines, or maybe continuous learning shared across a fleet.
Exactly. This opens up entirely new domains. Machines could have senses tuned to problems humans can't easily perceive at all. Think about analyzing global weather patterns from vast satellite data streams, or understanding the incredibly intricate folding of protein molecules, which is key to biology and medicine. They could even potentially understand high-dimensional mathematical spaces in a way that our three-dimensionally evolved brains struggle with. This really transcends the limitations of the old Turing test, which was only aiming to replicate human-like behavior. This is about building systems that can genuinely understand complex realities, maybe even ones we can't.
So the potential seems enormous. But what about the risks? Should we build them? Hawkins argues quite strongly that they will be one of the least dangerous, most beneficial technologies we have ever developed. Why is he so confident?
Yes, he's quite optimistic. His reasoning is that the common fears, the self-aware, malevolent robots taking over the world, are based on a fundamental false analogy. That analogy mistakenly conflates intelligence, which Hawkins views as the neocortical algorithm of memory and prediction, with the emotional drives and survival instincts of our much older limbic brain systems, the things like fear, paranoia, greed, desire for power. Truly intelligent machines built on cortical principles won't inherently have these drives unless we deliberately and painstakingly design them to. Why would we? He sees them primarily as incredibly powerful tools, extensions of our own minds that will help us accelerate scientific discovery, explore the universe, understand our own biology, and ultimately make the world safer and more prosperous.
So intelligence doesn't automatically equal human-like drives or emotions. That's the key distinction. Well, this deep dive has truly unpacked a revolutionary way of thinking about intelligence. It shows us that our brains are not computers in the traditional sense, but these powerful hierarchical memory prediction systems constantly building and refining a model of the world. It's a really A beautifully elegant framework when you lay it out like that.
It really is. And if we connect this to the bigger picture, you could see the quest to understand the brain and build intelligent machines based on its actual principles as a logical, maybe even necessary next step for humanity. It kind of embodies Carl Sagan's belief that understanding something scientifically doesn't diminish its wonder or beauty. If anything, it deepens it. We can now genuinely envision a future where intelligent machines, operating with custom senses and maybe that superhuman speed, help us solve problems currently far beyond our grasp, dramatically expanding our knowledge of ourselves and the universe.
And for you, the listener, I hope this deep dive leaves you with maybe a provocative thought to chew on. The very predictability that our brain constantly seeks, the thing that defines our sense of reality, is also the fundamental source of our understanding and our creativity through analogy. What new patterns, what new analogies, what new predictions might you discover in your own world if you started consciously looking for them?